So I think we can start for today's live interactive session. Okay. So welcome to all the students on this live interactive session on NPTEL online certification course on chemical engineering thermodynamics. So it's almost like we are going to be towards the end of this course. And I think already the week 12 content has already been uploaded into the NPTEL Swan portal. So we'll be having, like, apart from this live interactive session, we'll be having one more live interactive session next week. That will be the last live interactive session. Okay. So what we'll do today is that we'll cover up all the week contents and some of the assignment problems. So today we'll be going to do some of the assignment problems which has been discussed during the week 11, and solutions is already been uploaded, but we'll try to solve it out during this live interactive session also. Okay, so warm welcome to all the students and a very good afternoon to one and all on this online certification course on chemical engineering thermodynamics. So, like, just for a quick view, so this course has been offered by Professor Kavi Das. He is a professor in the Department of Chemical Engineering, IIT Kharagpur, and like I have been taking your live interactive sessions, I am a teaching assistant / Kushum Kumar. I'm a peer mark scholar in the Department of Chemical Engineering at IIT Madras. Okay, so this is the week 11th, and we have already covered through, like, most of the contents from the undergraduate course of chemical engineering thermodynamics 1, and we are almost towards the end. Almost like 2 weeks are planning this week, and the next week will be there for, like, completing the course content, and there will be your final examinations. Okay, so what we'll do is that we'll try to see the content which has been covered during the week, and then we will try to see what we can do for the last live interactive session that is going to happen in the next week. So today what we are going to do is we are going to cover up the entire week content. We will go through the week contents, and then we will see what to do furthermore for the next week. Okay, so if you see the week content for this week, for the week 11, is that just one sorry. So this week contents are somewhat like this, as it's based on the NPTEL portal. So the first one which has been discussed is related to the control mass analysis and the control mass analysis for the transient process. So entire topic related to the volume analysis, the mass analysis, and how its mass analysis can be done using controlling in the mass analysis in the transient processes. And also similarly, there are a discussed term which is known as a control volume analysis that has also been discussed in the week content, and the throttling and its problems. Okay, so the other things apart from this throttling processes and control mass and volume analysis, the contents which are covered are the first law for reacting system, estimation of standard heat of reaction, estimation of operating variables in the heat of reaction. So it's like I'm not going to go through the entire contents like in the theoretical manner, but we'll try to solve out some of the numerical problems which has been discussed in the week 11 assignments. So the first thing that has been discussed. Okay, so before going to the before going to, like, starting directly with the week 11 content assignment problems, we'll just try to brush up some of the things, like the last week up to week 9 and week 10. So we're discussing related to the absorption problems like isotopes, maximum boiling isotopes, minimum boiling isotopes, and we have seen some of the numericals, like related to the activity coefficient models in non-ideal solutions, like the Van Laar equations, Markow's 2 suffix 3 suffix, and non-Adam 2 liquid NRTL equations. Okay, so just to classify, means the different terms, like we have been also been covering different terms like extraction, distillation, leaching, and we have discussed and I already explained, like, what these different terms means about in, like, in the form of a match the columns. So this is one kind of an example which can be asked in the final examinations, but this diagram is much more relatable to somewhat we have already discussed. So the first question is, given below is a phase equilibrium diagram which is typical to. So now, if we have gone to the lecture notes and the live interactive sessions which have been covered, and I've already explained what this diagram corresponds to. So this A, B, 3 are corresponds to the three different components in the mixture. They might be miscible or immiscible with each other. Like A and B forms an immiscible mixture, and A and C forms a miscible mixture, but the others are immiscible in each other. But if you see this curve and the lines between it, they have the different meaning. So it's connect the extract and the raffinate phase, and this is known as a binary solubility curve. Okay, and this term is specifically related to known as an extraction, that is known as a liquid extraction. So the typical answer for this is in this guy. Okay, so this is related to the extraction term. In the absorption, we have already covered, like in the countercurrent mode, how the gases will be passing and how the liquid will flow in the countercurrent mode in order to particularly absorb one component from the gas into the liquid, and how to attain. Distillation is somewhat like I have discussed in the distillation column can be split in different forms. Like for the simple distillation column, the feed will be at the center point of the distillation column. The rectification section is in the top of the column, and the stripping section at the bottom. It's just like doing the rectifying of the vapor component, so the vapor going from the top to the condenser and then display, and similarly from the bottom is the stripping of the vapor, less volatile components. Okay, so now this question, these are questions can be asked and has been asked most of the times in the GATE as well as NPTEL examinations. So just like I've been saying, like different terms like rectifying, stripping, absorption, extraction, leaching. So what this term specifically mean about? So like the rectifying section has been covered and it is related to a distillation column. So in the distillation column, rectification terms relate to the vapor and liquid, because in a distillation column, if you see, this is your distillation column and here is the feed. We will take F XF, and here it will go to a condenser. Some part of it will be reflux and some part of it will be distillate, DXD, and similarly some part of it will be sent to the reboiler, and some part will take an WXW, that is raffinate. Okay, so this is how the distillation column works. Okay, so rectification is the top part. This part is known as the rectification, and this part is known as the stripping, and this part is rectification or rectifying section. Okay, so it's related to the vapor and liquid. Similarly, absorption is related to the gas liquid. So if you take an absorption tower, so there will be like two different modes, either counter current or co-current. If I say gases are flowing in this direction, oh sorry, okay, so this is in the counter current mode, and absorption is related to the absorption of a particular gas component for using a solvent. Okay, so the solvent will be as there is a pure solvent, and we will use in the counter current mode. So there are different types of absorption towers in which the gas and the liquid flows in counter current mode or co-current mode. So counter current is like this kind, this is in the same opposite direction, and co-current is in the same direction. Okay, extraction. Now in extraction, we know that the extraction relates to the liquid and LLE, which is known as liquid extraction. The last term is is leaching. So leaching is solid liquid. So the typical example which I have given for leaching is that, like in every household, like if you used to make a tea or a coffee, we have like tea bags or coffee bags, right? So what we'll do is we will try to squeeze that tea extract from the tea bag into the your tea mug. So that extraction of tea from solid, tea extractant from the solid is known as a leaching, that is a solid liquid operation. Okay, so this is a typical example which you can remember. So the correct answer is D. Okay, so these are just the terms I want to just like to do one quick view. I'll go to another one. So these are related to this week 11 assignments or problems, and we'll try to solve it out. Okay, so the first question is, during absorption of a component I from gas to liquid phase, the mole fraction of component I in the gas phase is Yi, and the equilibrium mole fraction of component I in the gas phase is yi star. Absorption coefficient I ceases when? Okay, so we have a component I whose equilibrium composition, oh, sorry, this is mole fraction. Mole fraction of component I in gas phase is yi, and it's yi star in, or the equilibrium mole fraction in gas phase is yi star. Now the absorption coefficient I ceases when? So the mass transfer of component I from dash to equilibrium ceases when it's attained. That is, so this will be ceases when yi equal to yi star. That means mass transfer of component I from gas to liquid phase ceases when equilibrium is attained. That is, a transfer of mass from the gas to the liquid will stop when the mole fraction of the component I in the gas phase equal to mole fraction of component I in the equilibrium phase. That is yi equal to yi star. So the correct answer is B. So this is the simplest one. Just need to know what is the equilibrium terms means about, and when the mass transfer will cease. That is, the both will have the same composition, and that composition occurs when the component I will have the same composition as under the component I in the equilibrium phase. Okay. We move to next question. So the next question talks about a rigid tank. A rigid and insulated tank of volume 2 meter cube contains an ideal gas at 0.1 megapascal and 300 Kelvin. The tank is connected to a pipeline carrying the same gas at 4 megapascal, 500 Kelvin. Okay. The valve at the top of the tank is open for the gas to enter to the tank till the pressure reaches 4 megapascal and then closed. By this process, the final temperature of the gas inside the tank reaches this much temperature, that is 677.62 Kelvin. Estimate the amount of the gas that enters the tank. Okay, we have to determine the mole fraction of the gas that is entering the tank when the temperature is attained inside the tank at 677.62 Kelvin. Okay, we'll proceed with that. So, I will write. So this is an ideal gas. Gamma equal to 1.4. So pipeline is 4 megapascal and temperature is equal to 500 Kelvin. While at the top of the tank, pressure is 4 megapascal. Okay, so what we'll do, so amount of gas that has entered the tank, so for equal to P naught 3 upon RT naught. We'll simplify this equation. Tf by Tf minus T naught by T naught. We'll try to pull it all over. So volume is given by 2 meter cube. R is 8.31451 joule per mole Kelvin. Final pressure is 4 megapascal. That is final pressure is 677.62. Initial pressure is given to us as 0.1 megapascal. So 0.1 into 10 to 6 divided by T naught is 300 Kelvin. We'll try to solve this out and you'll find out the final. So it will come on 1339.83 mole. So this is the final concentration. So what is been asked to us is the final temperature of this. Tf is equal to 677.62 Kelvin and T initial or T naught. Okay. So estimate the amount of regulated enters the tanks. In mole fraction, its correct answer is 1139.83. So this is the correct answer. Okay. So this is one of the simplest ones. Just need to identify how to do the how to relate this ideal gas law with this equation for control mass or control volume types. Now we'll try to move on to the next question. So these are two different questions and we'll do the both right now. So the slope of ln p versus ln t for an adiabatic process. So now I have like two different plot. If you take ln of p and ln of t and the pt diagram, the slope of that what will be. So it's related to the processes like we have already discussed in in week 1 and week 2 starting, but it's just for memory. So if you take in an adiabatic conditions, so I will try to write it out. For adiabatic condition, Tp raised to 1 minus gamma by gamma is equal to constant C. And also we can write Pt raised to gamma by 1 minus gamma is equal to constant C. If we take ln of P, it will be written as gamma upon 1 minus gamma ln of T plus constant C. So the correct answer is D, that is gamma upon 1 minus gamma. Okay, the slope is y equal to mx plus c. If we take m is this guy, that is gamma upon 1 minus gamma. So this is the correct answer, gamma upon 1 minus gamma. This will be okay. In order to just like rearranging in the equation, it's correct now. So gamma upon gamma minus. Now the second one is the reversible adiabatic process is. Now the reversible adiabatic process. Now this thing is related to something which known as an entropy, that is S is equal to Q by T or ds equal to del Q by T. The entropy of the universe continuously goes on increasing, but for a reversible adiabatic process, it is a constant entropy, that is the isentropic process. So the correct answer is B. So the detailed thing is, for the reversible process, T ds equal to del Q. And from the second law, since the adiabatic process, now we know that in adiabatic process, there is no heat flow in and out of the system, implies Q equal to 0. So this terms have to be 0 and ds equal to 0 for T not equal to 0. So the is a constant entropy, that is known as an isentropic process. Okay. Now we'll do the next question, which is related to the match the following. So the first one, if you go through, is related to the match the polytropic process indicated by the curves in the figures with the process named in column 2. Okay, so we have been given this figure and we have to relate the process related to the process named in the column 2. So if you see the first curve, that is A dash, we have been asked to relate this curve into the figure. So A dash corresponds to constant pressure. Since the pressure is constant, you can see this line. Okay, so if you take the plot, this is pressure and this is volume. Okay, now this is a dash, this is a constant line at a particular point. So this is as p1, so the pressure is constant, so we can say is an isobaric. This constant pressure is isobaric process. Okay, now b dash, where is b dash? B dash is at a constant volume, so b dash is this b dash b, so it's termed as isometric, that is constant volume, or isochoric. So constant volume terms are also known as isochoric or isometric, because this is at a particular point, and suppose v1. Okay, so these are the constant volume but variation in pressure. Now the third is c dash. So c dash is uh, is given as n equal to 1. So c dash is known as an isothermal, and d dash is along n equal to gamma. uh, yeah, n equal to gamma is known as adiabatic. Okay, so this is for n equal to 1 is isothermal, n equal to gamma adiabatic. Okay, cc dash n equal to 1 and this. So the correct answer for this guy is a1 b3. Yeah, this guy. So it's just like identifying what the different terms means about. So like I've been saying from the week one itself, is if you don't know about the specific terms, it will be very difficult for you guys to identify, solve some of the numerical problems. So this is one set of question, like one type of question which can be typically asked in the final examinations. So just remember with different terms once about it. Isobaric means constant pressure. Isochoric or isometric means constant volume. Isothermal means constant temperature. Uh, Adiabatic means constant heat flow, that is no heat flow in and out of the system, that is Q equal to 0. Isentropic means constant entropy processes. And isenthalpic means constant enthalpy. So these are like 5 to 6 different terms. Please remember what these terms are specifically meant about. So that it will be helpful for you from the various numerical to finally arrive at an answer. Okay. Now we'll move on to the next question. So a part of the a wet steam from the main at 5 bar is bled into a throttling calorimeter. Steam at throttling is at a pressure of 1 bar and a temperature of 110 degrees Celsius. Determine the quantity of steam in the main line. So we have been given a steam at 5 bar, molar enthalpy of the saturated liquid and molar enthalpy of saturated vapor we have been given to us. That is this and this at 5 bar. And the molar enthalpy of superheated steam at 1 bar and 110 degrees Celsius is given to us. So this one is the simplest one, just need to, it's like the throttling processes and its associated problem which has been covered during the week content, which this problem is related to that. Okay, so now we know that as throttling is an isenthalpic, like I told, what is isenthalpic is constant enthalpy process. Therefore enthalpy of 5 bar is equal to enthalpy of superheated steam at 1 bar and temperature of 110 degrees Celsius is equal to 2691.2 kilojoule per kg. Okay, now we know that enthalpy of wet steam is equal to x H1 plus 1 minus x H enthalpy of the liquid. That is the vapor, HV for the vapor and HF for the liquid. Therefore, 2691.2 is equal to x. We don't know the mole fraction, but we know that the HV is given as in the quotient 2747.5 plus 1 minus x. HL is given to us as 640.1. Therefore, from this, by solving this question, you can find out the value of x, that is 0.973. So, therefore, we need to find out the quantity of steam, that is x. This in the mole fraction is 0.973. So, this is the answer. Okay. Now, since this is a throttling process, that's why we have taken directly into consideration of isenthalpic process is constant enthalpy, and we have taken the enthalpy of the wet steam at 5 bar that is equal to the enthalpy of the Sotto steam at 1 bar. So it turns out to be 2691.2 kilojoule per kg. Okay. Okay, so guys, there was like disruption in the internet. Okay, now we'll move on to the next question. Like we have already done this question, I will try to solve some of the concepts. What is the throttling process and that all. So the first thing is like during throttling, the temperature of a real gas is dash while the temperature of an ideal gas is this. Yeah. Now I say like a throttling process is known as a constant enthalpy. That is isenthalpic process. Okay. So during the throttling process, the temperature of a real gas. Now we are talking about the real gas, not the ideal gas. So during throttling process, the temperature of a real gas decreases and that of an ideal gas does not change. So the correct answer is C. Why? Because during the throttling process, the pressure reduction and then in the atmospheric condition causes cooling of the real gas that does not change the temperature of an ideal gas. So this is the main reason. Okay. So it changes. So what happens? The temperature of the real gas decreases. It happens in the decrease in the temperature of the real gas, but that of the ideal gas doesn't change. Okay. Similarly, a residual adiabatic process. So it's like repeated, but it's like isentropic. I already discussed that is ds equal to dq by t. Adiabatic is this is 0. ds tds equal to 0. So ts equal to 0 at temperature not equal to 0. That is isentropic, is constant enthalpy process. Okay. We move on to the next one. Now this one is interesting question. We will try to solve it out. Which among the following equations denote a formation reaction? Okay. Now in order to infer the reaction is in formation or what, we will try to write it out. We will try to go step by step. The first one is C2H4 in the gas phase plus 2 in gas phase give ethanol C2H5 OH in gas. Now this is not a formation reaction because here ethanol is formed from compounds, not from the elements. Okay, so the formation reaction should be happening like it should form from elements, not from the compounds. So this is not a formation reaction. If you consider B, so this is carbon plus hydrogen and the gases plus oxygen in gas phase gives methanol. that is CH3OH. So like I said, the formation of reaction can only be classified if the reactant or the product that is formed from the elements, not from the compounds. So this all here are elements, carbon, hydrogen and oxygen. So this is a formation reaction actually. So this one is a correct answer instead of one. Similarly, if you go to C and D, you will see that they are formed from compounds, not from elements. Okay, now here also in the D option you can say this can also be a formation reaction. But here oxygen exists in a monatomic form, not in diatomic form. But oxygen in its elemental form exists in diatomic, that is O2. So this can also be not be considered as a formation reaction. Okay, so this is the correct answer. So formation reaction, product formed by reactants involving only elements and not compounds. Okay, so this is the simplest one in order to identify whether the reaction is in a formation reaction or not. And last, like I said, for the D1, oxygen is not in diatomic form, it's not an elemental form, because oxygen in its elemental form exists as O2, that is a diatomic molecule, but here is given in monoatomic form, that is O. So this, even though this reaction is wrong, which is H2 plus half O2 has to give H2, this is even O. Okay, so please remember this type of equation. If there is a mistake, don't try to just blindly take it the correct answer. Okay, I'll move on to this one. Okay, so the industrial important water gas shift reaction is given by carbon monoxide plus water give carbon dioxide plus hydrogen, that is CO plus H2O gives CO2 plus H2. This is well known reaction. It is known as water gas shift reaction. Determine the standard reaction at temperature of 298.15 Kelvin from the standard molar heat of combustion data. So we have been given standard molar heat of combustion data, that is for carbon monoxide, and for the hydrogen, latent heat of evaporation of water is given to us in kilojoule format. So the combustion reaction, we will write what is combustion reaction first of all. CO plus half O2 gives CO2, H2 plus half O2 gives H2O, and H2O liquid gives H2O gas. So this is A, B, and we have been given the standard molar heat of combustion data, that is the LHC of CO is equal to minus 283.18 kilojoule. This is minus 286.03 kilos. Okay, now we have like A, B, and C gives CO in gas phase plus H2 in gas phase gives water gas shift reaction CO2 in gas phase plus hydrogen in gas phase. Therefore, standard heat of this is standard heat of standard molar heat of combustion data at 298, that is at room temperature, is given to us minus 283.18 minus of minus 286.03 minus 43.966, that is given to us. This comes out to minus 40 minus 41.116 kilojoule. So this is the actual answer. Okay, so what we have done, we have taken the standard molar heat of combustion data of carbon monoxide, hydrogen, and then the delta to the water, and we find out the standard heat of reaction at 298 Kelvin, that is at room temperature. Okay, so this the correct answer turns out to be minus 41.116 Kelvin, that is in negative. Okay, so this sums out to be the week 11 content. And this is what I have for like this week. So what we'll be doing is that now the remaining thing is that only for the week 12. So the next week what we are going to do is that we'll try to summarize the entire course content. Like I will choose some of the numericals from like week 1, week 2, week 3 until week 12. We'll try to do most of the numericals, like combining all like one important numerical from all the assignments, and like we'll try to see if there are any issues or any problems related to some of the content which has already been covered till now. So next week our main task will be to summarize the entire chemical engineering thermodynamics one course into a nutshell, and we'll try to cover all the numericals or the week 12 assignment problems also probably. But most probably I will do try to cover up most of the contents and the numericals which we have already been discussed, but I will try to solve it once again in the week 12 content. So till then, if you have any issues, please do let me know, because final examinations dates are already been declared, I think so, and we have already been receiving the mails. So it's good. Please go through all these live and tech sessions. Please go through all the numericals that you are solving in this live and tech sessions, because it will be helpful for you in the final examinations to achieve good marks. And I will make sure that you will get good marks after going to this live and tech sessions, because we have been covering most of the contents, week contents every time, and we are trying to solve out some of the numericals what has been covered during the week. So it will be much more helpful to you guys if you go to the live and tech sessions apart from the live and tech contents of the NPTEL SWAM portal. So if you have any problems, any issues related to the course, still you have like 1 or 2 weeks to rectify that thing. Just go through all the contents that has been uploaded into the NPTEL SWAM portal. All these videos have been recorded and uploaded into the YouTube, and the links has been provided in the portal. Along with that, all the things in the PPT format has been uploaded in the PDF format in the same portal. So you can go and download the PPT in the form of PDF format, as well as you can go through the YouTube videos that is going to be uploaded on the same day. Okay. Till then, we'll meet you next week at the same time, 3 o'clock, for the last live interactive session of this chemical engineering thermodynamic course. Okay. Thank you. See you guys. Thanks for joining this live interactive session. We'll meet you next week. Thank you.